Hey guys, this is our final problem in the work and kinetic energy chapter. The problem description here is pretty long, so I'd like to take just a moment to briefly summarize everything that it's saying. That way we're all on the same page on what it's telling us and how to use that to get to the solution. A couple things are provided here about the air resistance of an airplane, how it's proportional to velocity squared, as well as this additional resistive force due to the air acting on the wings. The effects of the total air resistance can be described by this generalized force equation, but the constants in it, alpha and beta, depend on the characteristics of the airplane involved, as well as the density of the air. Let's apply this equation to a very specific type of airplane, a Cessna 150, which has the following measured values for those constants. Here are the two things that we need to do. In part A, we need to find the speed that provides the plane with the maximum range or distance for the fuel that it carries. And similarly, in part B, we need to find the speed that allows the plane to remain in the air for the longest amount of time. In case you're curious, here's a picture of what a Cessna 150 looks like, as well as a vector diagram of the relationship between lift, induced drag, and the force of the air acting on the wings. Now, if we want the speed resulting in the greatest range, let's think about how we can relate this to our work and energy concepts. The plane's engine has to provide some forward force to balance the air resistance in the opposite direction. And the engine will exert that force over some displacement. That means for a finite amount of fuel, the engine can perform some maximum amount of work, which we can label as W plane. We don't know what the forward force of the engine is, but since it balances out air resistance during flight, we can use the air resistance force equation from earlier, and that's going to be multiplied by the range. The plane can't refuel mid-flight in this problem. So again, this represents the maximum amount of work it can do before all the fuel is used up, and that is a constant number. If we want to maximize the range, but the left-hand side has to remain constant, the only way that we can do that is by minimizing the force of the air resistance on the right. The question is, well, how can we do that? What are we supposed to do? Well, we can take a derivative of the air resistance force with respect to velocity, set it to 0, and then solve for the necessary speed in order to make that happen. Let's go ahead and plug that expression in. All we need is the derivative power rule to do this derivative, which gives us the following when applied correctly. Let's move the beta term over to the other side to make it positive, then divide both sides by 2, as well as alpha. We want to solve for v, so let's also multiply both sides by v cubed. We'll need to get rid of that 4 in the exponent, so we can raise both sides to the power of 1/4, and now we have just plain v. Let's go ahead and plug in our numbers, since this is being expressed in terms of everything that we know. On my calculator, I get the following result. We're not quite done though. First, let's convert this to the required units of kilometers per hour. We'll multiply by 1/1000 kilometers per meter, as well as 60/1 seconds per minute and 60/1 minutes per hour. I get around 118 kilometers per hour as a result. I'm going to add a cautionary star here because the official solution misses a step and calls it done here. Remember, you cannot divide a value with two significant figures by another with two significant figures and end up with a result that has three. That's fabricating accuracy, and we can do much better than that. Therefore, the correct way to report this is to use two significant figures. So 120 kilometers per hour. The zero here in this number doesn't count as significant. So we are good to go. And there is our answer to part A. For part B, let's go back to our initial thoughts of work done by the plane's engine. To maximize the amount of time that the plane stays in the air, we would need to minimize the rate at which the fuel is consumed. We saw earlier that the fuel available to the plane corresponds to a maximum amount of work it can do, and the rate at which work is performed is power, which is just the product of force and velocity. So that means if we take a derivative of the plane's power with respect to v and set that equal to 0, we can figure out the necessary speed that results in the lowest rate of fuel consumption, which will keep the plane in the air for the longest amount of time. When we multiply our air resistance force equation by v, it will change it slightly, but the process of solving for v will be exactly the same like we did in part A. You apply the derivative power rule first, then move the beta term over to the other side, get your v variable isolated on the left by multiplying both sides by v squared, and then divide both sides by 3 alpha to put everything else on the right. We'll take the 1/4 power of both sides again, and now we're free to plug in the numbers. I get the following. We'll have to convert from meters per second to kilometers per hour again, and that's done in the same way. There's nothing new there. And we'll take our result and round it up using two significant figures to 90 kilometers per hour. But be sure to use scientific notation to express that. The plane number 90 only has one significant figure in it, so you'll be short if you don't use scientific notation. With that, our work chapter is now complete. Have a good afternoon, everybody. I'll see you all in the next one.